So welcome back to our lecture series on circuits and networks. So today we are on the 18th video lecture, and in this lecture we are dealing module 2, and in which the last class we were discussing about a RL and RC circuit which are excited by a DC source. And it is not only just an RL or RC circuit. We are doing some switching actions in the circuits. So such a circuit is known as dynamic circuit or transient circuit. And we in detail discuss the general things like how we can derive the response equation in case of an RL circuit with purely inductor and with some value of resistance, and what may be the voltage of current, what may be the equation for current, or what may be the expression for voltage. All those things are derived, and from that response we obtained initial value, final value, y0 and I of 0, I of infinity, and v of 0, v of infinity, and we plotted the exponential curves also. Not only the RL circuit, both RL and RC circuits were discussed. So now this is the time for doing some problems from that derivations. Okay, so before going to that, let me have a brief discussion about the final conclusion of an RL and RC circuit. What may be the state of an inductor in case of steady state in RL circuit, or what may be the state of inductor during transient period in an RL circuit. Such things we already concluded in the last slides of the previous lecture. Now I am just recapping those slides. This was the final conclusion of an RL circuit. So RL circuit means generally the main thing that should come to our brain is presence of inductor. An inductor will not oppose sudden change in current, whether it is AC or DC. An inductor will not oppose the sudden change in current. So we can see the current waveform that how we will draw this waveform. For that we have to derive the current equation. Those things are there in the video lecture number 16. You can refer. So now when the current, initially the switch was open, so the current value was 0, and at the time of 0 instant the switch is closed. Current is gradually increasing towards its final value, and its final value was E by R, final value of current. So we should be very careful that I0, that is nothing but the value of current at the 0th instant, is equal to I0 minus and I0 plus. What is I0 minus? The current just before the switching instant. And what is I0 plus? What is I0 plus? It is the current just after the switching instant. So I0 minus and I0 plus are same. Why we are assuming it is same? Because the change is very gradual in current. So that we can assume, even though there is change, that change is very gradual, and these 3 points are very close. So we can say take I0 minus is equal to I0, that is equal to I0 plus. But in case voltage in inductor, it is not like that. Voltage is having a sudden jump. Up to the moment when the switch is open, initially the voltage was 0, and then while the switch is closed, the initial voltage suddenly jumped to high value. How you will get that? Voltage value at time is equal to 0 is a very high value, that is E. In the figure you can see it is E. From where you will get that? You have to put T is equal to 0 in our voltage equation. Please refer video number 15 if you are not aware about this. Okay. Then sudden jump is there at the 0 instant, and after that the current is exponentially reducing to its final value. So what are the conclusions? During the switching period, that is during the switching period means this region switching period, time is equal to 0. During the switching period, voltage is high and current is 0. Voltage is high and current is 0 means it is equivalent to a open circuit. Current is 0 mean open circuit. So during switching time, inductor acts as open circuit. That is not that much important for us to do problems. In problems, steady state condition is very much important. I will explain. So please look at an instant which is very please look at an instant in the infinite region. This is not the infinite region. Anyhow, the time will go towards infinity at some time, and at that time the current value will be very close to E by R or final value. Anyhow, at steady state reaches at some time. I don't know when exactly it will reach, but anyhow, the value of E by R is very close now itself, and after some time it will become exactly same to that dot line. That is known as steady state. Now it is somewhat closer to steady state. In the figure, this instant is somewhat closer to steady state, but after some time this will exactly touch. So we don't know when it will exactly touch. That's why we are generally putting T is equal to infinity, because at infinity anyhow it will touch. Definitely it will touch, because infinity is a time very far away from the from that point of this point of time. Okay. So anyhow, for steady state we can see the current value is very high and voltage value is very in the figure. This is the maximum time point. So here current value is very high and voltage value is very small. That is equivalent to a short circuit. So inductor acts as a short circuit in steady state. Inductor acts as a short circuit in steady state. This is very important conclusions for doing problems. Now we can solve problems. Okay, before doing problems, I will once again repeat the steps of derivations we already did in the RL circuit and RC circuit are very important. The same step we will follow in all problems, because no standard results are there. Because you are drawing switch from 1 to 2, 2 to 3, you may be putting 1 or 2 switches. So the questions in the question paper will be entirely different from the standard derivation that we have did in the 15th video lecture and 16th video lecture. These two lectures contains only standard derivations, how to charge a capacitor, how to discharge a capacitor, such things, capacitor and inductor. Such things are there, but in problem it will not be exactly like that. We have to find the current expression and voltage expression. You can use the exact equation that you obtained in the derivations. So in each problem you have to develop the function of current and voltage. For that, the steps that you proceeded in that derivation, RL circuit and RC circuit, that derivations are very important. The same steps we will be applying in all problems. So if anybody didn't familiar or didn't watch that last videos, lecture number 15 for RL circuit and 16 for RC circuit, sorry, I think 16 for RL circuit and 70 for RC circuit, please watch it once more or again. Then only you will get the clear idea about the steps that we are using in solving such problems. Okay, now please read the problem. In the network, the switch is initially in position 1. On the steady state having reached, the switch is changed to position 2. Find the current IT. So initially initially the switch is connected to position 1, and that condition is kept for a long time for obtaining or for reaching steady state. You are not permitted to move the switch without reaching steady state in position 1. Initially the switch is in position 1 and you are waiting till the steady state is reached. Steady state is attained in position 1. Then only you are permitted to move to position 2. So for that, the condition of steady state is very important. That's why I already discussed those slides as a first slide in this today's lecture. Find the current IT. So initially switch is in position 1 and after attaining steady state in position 1, switch is moved to position 2. What do you mean by steady state? You are waiting for enough time, so all the transient condition will cancels and finally it will reach a steady state value. That is known as steady state condition. So after steady state or otherwise only after reaching steady state in position 1 you are permitted to move the switch to position 2. So we are redrawing the cases. At t is equal to 0 minus in position 1. What do you mean by 0 minus? Because at t is equal to 0 we are going to turn the switch to position 2. At t is equal to 0 you are going to move the switch to position 2, assuming that is the instant where steady state is already obtained for position 1. Just like this. Initially you are in position 1. You are waiting for sufficient time for reaching in steady state. Then only you are moving switch to position 2. This instant of moving from 1 to 2 is taken as 0th instant, t of 0 or instant of switching. In any circuit, if there is a switching, always take the switching instant as 0 instant, 0 time, t of 0. So at 0 minus means at 0 the switch is drawn from 1 to 2. So at 0 minus where the switch is? The switch is placed at 1, position 1 itself. Position 1 now at t is equal to 0 minus position 1, the network attained steady state because you are waiting a long time in position 1. So definitely the network will reach steady state in position 1. So this is the general figure of position 1 because in position 1 we can see a voltage, resistor and inductor. This is the position 1. So this is the general case of position 1, but we know that in steady state inductor behaves as a short circuit. In the first slide we already discussed inductor behaves as a short circuit. So you can draw like this because the inductor should be replaced by a short circuit like this. Now please say what is the value of current? I0 minus. I0 minus is the instant just before the switching happens. This is 1 and this is 2. Initially at 1 and at time is equal to 0, switch draws to position 2. So at just before the instant of drawing the switch, that means switch is at position 1, I0 minus, that is equal to the blue color figure. Only things are V and R1. So the current value will be V by R1. And one more thing is that I0 minus is equal to I0 is equal to I0 plus because it is an inductor. Inductor will not will not admit sudden change in current. Now at time is equal to 0, you are just drawing switch to position 2. So what are there in position 2? We can check. In position 2 means this is the circuit. The voltage source is now not there in the circuit because there is no path for getting a closed loop with the voltage source. This is the one and only closed loop. So the circuit will become like this. R2, R1, L, and initially there was a current is flowing towards the inductor. So the same direction will be kept as inductor will not permit sudden change in current. So current is passing in the same direction. So plus and minus terminal polarities are marked based on the current direction, plus here, minus here, plus here, minus here, plus here, minus here. So a current is passing through the inductor at t is equal to 0, and the value of that current is the current which was already present there in the circuit, that is V by R1. Now apply KVL. Plus R2 into I of t. I of t is nothing but current as a function of time, plus R1 into I of t plus L into di by dt or diot by dt, that is equal to 0. Or with simply writing R2i plus R1i plus L di by dt is equal to 0. R1 plus R2 are taken to a bracket because I is common for both the terms. R1 plus R2 into I plus L di by dt is equal to 0. Now, in the derivation of RL circuit that we did in 15th video lecture, we know that we have to make di by dt is coefficient 1. So you should cross multiply with L or divide all terms by L. Then what will you get? R1 plus R2 by L into I plus L will cancel, plus di by dt is equal to 0. So you are dividing all the terms with the coefficient of di by dt in order to make coefficient of di by dt 1. Now you will get coefficient of basic variable I is R1 plus R2 by L. These terms should be taken for forming integrating factor. This is the same things we already did in the derivation. Follow the same steps, you will get correct answer. But the things will be different. R1, R2 will be different. Whatever components are there in the circuit may differ. You have to follow the same method, but not the same values. So integrating factor is equal to E into R1 plus R2 by L, because you are substituting this coefficient into here as an exponent, not as a total term. You have to substitute that coefficient as an exponent. So e raised to R1 plus R2 by L into t. You are making it in a common form of e raised to at, where a is equal to R1 plus R2 by L, that we obtained from the differential equation. So now we are multiplying all terms with integrating factor. E into R1 plus R2 by L into t into first term R1 plus R2 by L into I. This is the term already existing there, plus again integrating factor E into R1 plus R2 by L into t, again the existing term, plus into di by dt, that is equal to 0. This step is already known for us because this will give a standard differential form, differentiation of uv, differentiation of u into v. I will explain. So differentiation of u into v, where u is equal to e raised to R1 plus R2 by L into t and v is equal to I. That will give the previous step. So you should know this is the approach, otherwise you will take a lot of time here. You can check, if anybody having doubt, you can check is it right or wrong. D by dt of e raised to R1 plus R2 by L into t into I, that is equal to 0. On right hand side 0 itself is there. Now take R1 plus R2 by L is equal to P, only for avoiding the time for writing the huge exponent. If it is P, we can save some time and we can make the steps looking simple. So R1 plus R2 by L is equal to P. Now you can rewrite that big equation as d by dt, in that dt is cross multiplied. So d of e raised to pt, p is substituted, into I is equal to 0. 0 is there, you please write that. Please write a 0 here. 0 here and here. Both the RHS is equal to 0. Now integrating on both sides. Integral of d ept into I is nothing but ept into I. Integration and differentiation will get cancels. Ept into I, that is equal to sorry, it's not 0. That is equal to, as the term in the above equation is 0, you are differentiating that 0, sorry, you are integrating that 0 because integrating 0 will give a constant. It is an arbitrary constant. If you are integrating 5, it will be 0. 10, it will be 0. So if you want to integrate that 0, you have to take any of constant. So e raised to pt into I is equal to arbitrary constant. So take it as an a, arbitrary constant a. Now divide all the, so please write here, here it is not 0, it is a. A is an arbitrary constant. Now divide all the terms by e raised to pt. So you will get I is equal to a into e raised to minus pt, because e raised to pt in the denominator is going to the numerator. I is equal to a into e raised to minus pt. So I of t is equal to I, simply it is I. Now I am writing it as I of t is equal to a into e raised to minus pt na. So p is against resubstituted. A into e raised to minus r1 plus r2 by L into t. To find value of a, we have to use initial condition, that is I0 is equal to v by r1. It is already obtained because it was steady state. Initially it was in steady state with position 1. So at that condition we already obtained that I0 is equal to v by r1. So substitute that. I of t is equal to I0, that is equal to v by r1, that is equal to a into e raised to, in the exponent there is a t. When t is equal to 0, the total equation will become v by r1 is equal to a into e raised to 0. So a is equal to v by r1. Now put a back to the equation of I of t, or I. So you will get v by r1 into e raised to minus r1 plus r2 by L into t for all t greater than 0. For all t greater than 0. Please write here, for all t greater than 0. So this is the answer. Suppose in that question, if you are having r1 is equal to 1, r2 is equal to 2, L is equal to 2, v is equal to 5, such values are given, then also you can proceed in this method and finally you can substitute those values, or otherwise you can do with the values from the initial step itself. That will also work fine. So if you are substituting in the final answer, you will get 5 into e raised to minus 1.5 t. Please check that. Now, in the network shown, the switch is closed at t is equal to 0. A steady state having previously been attained. Find I of t. Again, somewhat a similar question. Switch is already open. And we are going to close the switch at t is equal to 0. Switch is already open, but we are going to close the switch at t is equal to 0. A steady state having previously been obtained. That means with the switch is open itself, you obtained a steady state. And at t is equal to 0, you are going to close the switch. So before closing the switch, the circuit is in steady state. A steady state RL condition is there. Then you are asked to find I of t. So first of all, you have to go to the initial condition at t is equal to 0 minus. Now attained a steady state condition, because before the switch is closed, you are already in a steady state condition. Steady state means in RL circuit, inductor will act as short circuit. So please, this is the condition, switch is open. So remove this switch and remove the inductor with short circuit. So inductor acts as short circuit, switch is open. Now from that figure, we can point out what is I0 minus current in that circuit. There is a voltage source of 10 volt and 2 resistors are there. So I0 minus. Why you are taking I0 minus? Because it is the instant just before switch is closed. So switch or closer of switch. It is an instant just before closing of switch. That's why we are taking I0 minus. And that is equal to V by R1 plus R2. That is equal to 10 by 7. So I0 minus is equal to 1.42 ampere. And as it is an inductor circuit, current will not admit sudden change. So I0 minus is equal to I0 plus is equal to I0. That is already known. Now, for t is greater than 0, switch is closed. Actually, switch will be closed at t is equal to 0 itself. Generally, for t is greater than 0, anyhow, switch will be closed. You are writing KVL in this direction. So, minus 10 plus 2 into I plus 4 into di by dt is equal to 0. That is equal to, make the coefficient of di by dt as 1. So, divide all terms by 4. 10 by 4 plus 2 by 4i plus di by dt is equal to 0. So, by solving 0.5i plus di by dt is equal to 2.5. 0.5i plus di by dt is equal to 2.5. So, what is the integrating factor? Initially you made the coefficient of di by dt as 1. So, integrating factor is the coefficient of basic variable I. So, integrating factor is equal to exponent of that term. So, e raised to 0.5t. E raised to 0.5t. Okay. Now, e raised to 0.5t is multiplied at both sides. So, e raised to 0.5t into 0.5i plus di by dt into e raised to 0.5t. That is equal to, on right hand side, 2.5 into e raised to 0.5t. So, multiplication is over. Now, please check. It will be definitely in the standard form. Differential of two things. Differential of basic variable and exponent. In all such derivation, it will be appearing like this only. So, d by dt of e raised to 0.5t into I. If you are having any doubt, please solve this. You will get these things in the left hand side. D by dt of 0.5t into I, that is equal to 2.5 e raised to 0.5t. So, now I am cross multiplying dt. d of e raised to 0.5t into I is equal to 2.5 e raised to 0.5t dt. Now, integrating both sides without limits. In such case, the integration will be conducted like this only. So, e raised to 0.5t into I is equal to, because differential and integration it can get cancels, 2.5 e raised to 0.5t. If we are integrating, it will give 2.5 e raised to 0.5t divided by 0.5 plus a. This anti-differential term, we have to take a plus a with the result of integration. In all cases, we are taking like this. It is a constant. A is an arbitrary constant. It may be 5, 10, any such values. We have to find what is the value of a. Okay. Now, e raised to 0.5t into I is equal to 5 into e raised to 0.5t plus a. Now, divide all terms by e raised to 0.5t because we want I alone. So, I is equal to 5 plus a into e raised to minus 0.5t because e raised to 0.5t is there in the denominator. So, in the numerator, it will get a into e raised to minus 0.5t. Now, I of t is equal to 5 plus a e raised to minus 0.5t. To find a, use the knowledge about initial condition. What was there in the initial condition? We already calculated at position 1 or at I0 minus already calculated before the closure of switch. That is equal to I0 minus is equal to I0 is equal to I0 plus, that is equal to 1.42 ampere. I0 is equal to 1.42 ampere, already obtained in the first step of this problem. So, to find that, substitute I0 for 1.42, that is equal to 5 plus a into e raised to 0 because we have to put t 0 for all the t. So, here also e raised to some 0.5 into t. So, e raised to 0. So, a is equal to 1.42 minus 5. So, it will be minus 3.58. Value of a is equal to minus 3.58. Substitute that back into I of t equation. I of t equation was this, 5 plus a into e raised to minus 0.5t. This was the basic equation. Now, I am substituting a in that equation. I of t is equal to 5 minus 3.58 e raised to minus 0.5t. Okay. So, this is the expression for current. In this case also, you can do this problem by substituting all the values in the initial step itself, or otherwise you can take R1, R2, RL, L like that, and finally you can substitute the values of resistor, inductor, etc. in the final step, like we already done in last problem. These two approaches are right, but it will be somewhat easier if you are taking like this problem. If values are substituting in the first line itself, that will be more easier for solving. Anyhow, the one and only thing you will be very careful about are condition of inductor during transient period and short circuit, and also the steps, flow of steps that we done in the previous class for deriving RL circuit and RC circuit. So hope you all enjoyed this class. We will be meeting in next class. So before that, be very clear about the RL circuit, RC circuit and problems. First of all, you should watch the theory classes very well. Then only you can do these problems. So thank you. We'll meet in the next class.